We would almost always like to have control over different parameters of the process, like temperature, pressure, level, and so on. To achieve this, obviously we need a controller, like Programmable Logic Controller, or PLC for short. We also need some sensors and transmitters to send data over to PLC. Finally, we need a piece of equipment to carry out the PLC's commands, which usually called as final control element. A final control element can be a pump, a heater, a control valve, and so on. If you would like to figure out how control valves exactly work via an interesting practical example, stay with us to the end of this video. And if you like this style of video, subscribe and click the bell to receive notifications of new videos by Upmation. Very often by control valves, we mean the type of valves that are used not only to fully start and fully stop the flow, but also to control or adjust, or in other words, throttle the flow of the liquid. By throttling the flow, we achieve our final purpose, that is, for example, controlling the temperature of a furnace or the level of a liquid inside a tank. You may say how it is possible. Don't worry, we are going to talk about it in detail. Well, this is a globe valve, one of the most common types of control valves. Let's take a quick look at its different parts. This is the body of the valve that the fluid will pass through it. And this is the bonnet that is connected to the body and covers its inner parts. We call this part plug. The plug will control, stop, or start the flow by exposing the liquid flowing inside the pipe. This part here is the actuator that transfers the mechanical power to the plug using the stem. The actuator will receive the commands from the positioner. The main role of the positioner is to be an interface between the PLC and the actuator to precisely adjust the plug for being open or closed. There are a variety of actuator and positioner types, and we are going to check them all at the end of this video. So let's start with an example to understand the operation of the positioner and its relation to the PLC and actuator. In this example, we aim to control the temperature of a liquid within a tank by regulating the flow of an additive. This additive will generate heat by having a chemical reaction with the liquid already inside the tank. Say the PLC decides to send a 50% open command to the control valve. This command is based on two items. First, the PLC logic, and second, the feedback it has received by the temperature sensor installed on the tank. This command signal often is in the form of a 4 to 20 mA DC electrical current and is sent from the PLC. The device that receives this signal on the field is the positioner of the control valve. As we are using a specific type of pneumatic actuator in this example, which needs compressed air to become activated, therefore, we chose an Electro-Pneumatic Positioner. Don't worry about the names at the moment. In this case, the positioner plays the role of a translator and converts the PLC language to the actuator language. It means that the positioner will convert the 4 to 20 mA signal to an air pressure signal. But how it happens? Well, inside of this positioner, we have a converter unit which is called I2P transducer. In fact, this transducer converts the 4 mA DC current to a 3 psi air pressure and the 20 mA DC current to a 15 psi air pressure. And of course, they are proportional in the middle range. We call 3 to 15 psi air pressure as the pneumatic signal. So, with a simple calculation, we understand that in order for the PLC to open the valve for 50% of its full range, it should send a 12 mA signal to the positioner. Then the positioner will convert it to a 9 psi signal accordingly and will send it directly to the actuator. But wait, it sounds like the 9 psi pressure is not enough to move the actuator. Therefore, we need another input to the positioner as the air supply. The air supply input will provide us with a clean, filtered, regulated air with sufficient pressure thanks to this filter regulator device. After all, using the air supply input and a built-in pressure amplifier, the positioner will be able to convert the 9 psi pressure signal to sufficient air pressure for moving the actuator to the right amount. Now we see that the actuator is able to overcome its spring force, and so far so good. But same as the PLC that requires feedback by the sensor to decide about the command it is going to send, the positioner also needs to receive feedback to precisely position the valve stem and open the valve to 50%. This feedback is sent by the control valve to the positioner using a mechanical mechanism. In this way, the positioner will decide how much pressure the actuator needs to move the valve stem. In general, positioners come into 3 different categories. First, the Electro-Pneumatic Positioners, or I2P positioners, that we already discussed in the example. Second, the Pneumatic Positioners, in which their control signal is a pneumatic signal and they do not need any I2P transducer modules integrated. The last is Digital Positioner, or Digital Valve Controller. In addition to an I2P transducer, these positioners take advantage of a microprocessor to fill in the place of the mechanical position feedback. The input signal or setpoint from the PLC will directly send to the microprocessor. The valve position feedback, which is measured electronically, will also enter the microprocessor. Comparing these two electronic signals, the microprocessor is able to adjust the valve position quite accurately in comparison with the other types of positioners. Using digital positioners, we are able to communicate with the valve by different types of protocols, such as hard or field bus protocols like Profibus. By such digital communications, we can calibrate control valves way more easily using handheld communicators without tackling time-consuming and sometimes difficult mechanical adjustments. Besides, we can send some feedbacks from the control valve to the PLC or DCS via these communication protocols. The last point is that the standalone I2P transducers can control the valve independently in case that the accuracy is of less importance, meaning that they are not integrated into any kind of positioners and therefore there is no feedback in this case. Now that we've got introduced to the positioners, let's get into the actuators and their different types. Generally, we can classify the actuators into 4 different categories: pneumatic, hydraulic, electric, and manual. The pneumatic actuators are the most used kinds of actuators due to their simple design, fairly low price, and of course being intrinsically safe. Electric actuators have an electric motor inside. In the first place, they have been designed for on-off applications, but nowadays, some of them are upgraded for continuous control applications. The primary application of them is in the locations that we don't access the compressed air. In this video, we'll learn how a spring and diaphragm actuator, along with an electro-pneumatic positioner, adjusts the valve in order for the valve to control the flow of the liquid according to the PLC's commands. Well, it's time to ask us your questions or tell us about your experiences dealing with the control valves in the comments. Again, if you like these kinds of videos, please subscribe and tell us which subjects you are most interested in. Thanks for watching!